All right. So it's my pleasure to introduce you to Zifeng Guo. He is a visiting postdoctoral researcher at University of Florida. Previously, he was a postdoc and PhD student at ETH Zurich. And well, welcome.
Thank you, Carla. And yeah, I'm very happy to have this opportunity here to share a little bit of my work recently. So yeah, I will just get started. And yeah, the title of my talk today is an Archdaily Lexicon. So it's a search engine, the small search engine of Archdaily I developed for my PhD. And then so today, first I want to share you this search engine, but also because it's actually quite simple. So I was thinking maybe it would be interesting to also share the, let's say, the thoughts that kind of inspired me for develop this search engine, and then which kind of related with the relationship between architecture and artificial intelligence. So yeah, it's not playing. Sorry, it's not playing. Okay. Yeah, so Archdaily, I mean, as architect, you probably goes to this website a lot. And then this is how we search on Archdaily. So we have different categories by countries, by architects, by manufacturers, by materials, by areas, by the colors of the projects. So basically it contains many different categories that Archdaily provides us, and hopefully it covers whatever we want to search. And then my question about Archdaily, or this kind of way of doing search, is that what if our search is not there? So what if we are looking for something and maybe we don't have a clear clue how we describe the thing we want to search, and what if this thing is not included in these categories, and then what we want to do? Perhaps maybe the first idea we come to our mind is that, okay, then we include some new keywords to the website so that it becomes richer and richer. But then I realized that actually this may not be a perfect solution, or maybe there's another way of doing the same thing. So because by keep adding the different keywords, it reminds me that we are actually doing a kind of simulations to the reality, not just graphically, but also ontologically, which means we try to develop concepts that perfectly reflects our real worlds. So we have, yeah, like the materials used in architecture, we have woods, we have concrete, we have this, we have that. We try to include everything into a hierarchical order. And then I realized that this is the manner that how artificial intelligence in the last century, how they did it. And then eventually they kind of gave up this path. And then the idea was that, sorry. Continue, please. Okay. And then the idea was that, okay, since they already abandoned this way of doing, then is it possible that I can make a search engine that also try another alternative? And that's what this experience comes from. And yeah, and before I goes into the experiment, which is actually very simple, I was thinking maybe it's a better idea to quickly explain some of my observations between AI and architecture. So yeah, that starts with this part one, ontology making and the frame problem. So yeah, artificial intelligence, about artificial intelligence, so solving, we all familiar with artificial intelligence because it kind of solves many different difficult problems that we thought, okay, it would be very difficult for the computers to do it. So solving problems with computer comes from Turing's ideas of intellectual search. So basically, Turing proposed that whatever problem we encounter with, we can transform this problem to the manner of search for a number n such that blah, blah, blah. And then the idea behind is that if we can convert problem A to problem B, and then if we can solve problem B in the systematic manner, then that's done. Then the only thing we need to worry about is how to convert our problem into this specific problem that has been solved already. And Turing's idea is actually very simple to explain. This is a textbook example of puzzle solving. So for example, if we want to solve the puzzle on the left to another state on the right, then this is the steps that we need to do. So we just do this up, down, left, right operations, and then it's done. And then if we name these up, down, left, right operations in different symbols, different letters, then we have a kind of representative system that is very similar with how we represent numbers. So we have numbers of digits, like we have 10 digits representing the decimal numbers, and then here is very similar. We have 4 letters that represent a kind of numbers. Therefore, it's basically, so puzzle solving is basically finding a number spelled in the digits of these 4 operations. And then this brings to the idea of the search space. So basically, we have not just one sequence, but many different possible sequences. And then they constitute a tree-like structure that in this structure, we kind of navigate from one point through different branches until we reach to a point that our problem is solved. So this is basically it. And then when combining the idea of search with logic, then we have, for example, automatic serial proving in mathematics. So because mathematical expressions is essentially, text that can be converted from one to another following certain rules, and then these rules, we call them axioms. So following the ideas of logic and axioms, we can use the same idea to do automatic serial proving. And then in architecture, the same idea applies as well. So we have certain, let's say, input. For example, we say we set a size for our site, and then we want certain spatial relationship with the element we want to put into our site, and then the computer searches for all the possible solutions and gives us those that match these constraints. And then, of course, many of the architects actually proposed this in a manner that, okay, when we were designing, we were actually searching different alternatives until we reach to a point that we are satisfied, or the design match satisfies all the constraints, etc., etc. So they claim it like this, and then they describe it as if a search process within this design space. And of course, with the computing power, we can automate this process, and then we actually seize the computational process of this problem-solving process, and then we get obsessed about it. We are celebrating about it, right? And then these ways of doing things, one of the most prominent example of searching using computers is perhaps this application called Deep Blue, which is a chess playing program. And then in 1997, it defeats the Russian chess champion, Garry Kasparov, if I pronounce it right. And then because it's very simple idea behind this chess program, and then therefore people was wondering, okay, if this is the ultimate solution, then basically what we need is a stronger computing power, because if you can search faster, then we solve more and more difficult problems in the same manner. So what we need is the search power. But unfortunately, there's a phenomenon in mathematics called a combinatorial explosion, which claims that this is a dead end. So still, this is the example of these puzzle games, but then imagine if we increase the size of the grid for the puzzles, then we realize that all the combinations of these operations becomes enormously large. And then this is just for the very simple case. And then for the many different problems we can encounter in reality, then this search space becomes really, really large that we cannot exhaust them in a meaningful time. So that would be the bottleneck AI researchers encountered in the first place. And then because of this problem, then people was wondering, okay, so maybe it was the problem that the computers were not being able to, let's say, remember what was happened. So the computers was not able to gain any experiences from solving previous problems. And this is the hypothesis comes that, okay, perhaps this problem can be overcome by encoding human knowledge into the computer system so that the computer does not have to rediscover the word every time it tries to answer the question. It's like, for example, for us, if we want to prove some mathematical theorems, then we use those theorems that are already being proved as the, let's say, the preconditions for our work. We don't start from scratch. We don't try to prove those three theorems again. And then this is the same idea behind this claim that we don't have to, the computers doesn't have to, redo those works again and again and again. And then in terms of how to encode our knowledge, the most common way of doing it is to express them as as rules. So rules are essentially statements that can be expressed as if something, then something. So for example, if certain symptoms shows up, then we think that, okay, there may be a certain disease happening. And then again, in architecture, we see the similar efforts that tries to build rules for designing, for example. For example, here, there are rules talking about how should we choose the positions of the chairs or the colors of the walls based on the lighting sources we are using. And then we can design the rules not only by the text but also by the graphics. And then we produce a automatic program that produce this realistic cities, for example, from a very simple input. So we have the input, and then the computer program runs all these rules, and then it produces a very nice result. And then because the need of producing rules, then there's a thing called ontologies that shows up. So basically, ontologies are, let's say, are the effort that we cut our realities into meaningful parts, into parts that have semantic meanings, and we kind of organize these parts in a hierarchical order. And here is an example of about our world, and we also see similar efforts in architecture as well, like how to describe an architecture model in the way that it is not only the geometry but also semantic meanings that reflects the reality. So it started with this very simple example, and then it becomes a little bit more complicated, and then it becomes the building information modeling we see nowadays. So building information modeling is essentially an ontology that describes what buildings are about. So that you have doors, you have windows, you have columns, you have ceilings, and then there are certain relationships between these elements. So it's a category of things. So the question about the ontology making is that, so since we need ontologies to describe our words, then is it possible to, try not to reinventing the wheels? Is it possible to, just make one ontology that works for all the purposes? And this becomes a let's say a pragmatic question, because again, it's like reinventing the reproving all the mathematical theorems. maybe we don't have to redo all these process from scratch. Maybe we just take them and use it and try to make it, let's say, better and better. And there's actually an effort for that. So this is a project called SIG. So it is a project that is one of the largest projects on ontology making, with the ambitions to try to encode every common sense knowledge of the world, so that the computers can reason about some certain facts about our reality. So, for example, iPhone is a type of cellular phone, and then a cellular phone is a type of phone, and then the phone is a kind of consumer electronics, etc., etc. And then this project causes lots of discussions and debates on whether or not it is a kind of something that is crazy. And the reason that there's such debate is the problem called the frame problem. So the frame problem basically says that here's an example of the frame problem. So there was automatic program of the Ford Motor Company that was designed for credit analysis for the customers. So based on for example, the age of the customers, the type of the job of the customers, and then the salary level of the customers, and then these computer program decides whether or not we should issue the loans for these customers. But then this program fails for one of the applications who claim 10 years from the application from a 20-year-old who claim for 10 years of experiences. This is because that the age of 18 is the age people becomes an adult. This common sense knowledge is not actually included into this system, and therefore the computer system failed to reason about this simple fact. And then the problem becomes complicated because then we will soon realize that it is not possible to exhaust all the possible common sense knowledge into our computer systems, because we always find exceptions from that. So, for example, we can make a very simple claim that can birds fly, then we say all birds can fly, except something. And then in this exception, we can also claim another exception, and in the hierarchical order. And then we realize that first we cannot include all the possibilities, and then there's no fixed boundary of what kind of knowledge we should involve into even a very simple problem. So here is just a very simple claim, and then by exploring all these exceptions, then we realize that okay, we need to take these into consideration, we need to take that into consideration, and then this goes endlessly. And then the frame problem, the impact of the frame problem can be seen from this fact that, for example, that there's a debate between whether we should use more complex models or we should stay with the simpler ones. So, for example, the complex models, some claim that they depend on the parameterizations and the comparisons with data, and therefore without a large data set, complex models are simply randomly guessing. But then from the other side, they said that okay, simpler models may potentially inform about the phenomena in a certain level, but then it does not necessarily make a good prediction. I mean, both sides are true, but then what can we do about it? And also in architecture, we see these different ontologies that is fighting for being, let's say, the one that everybody should use. So we have the industry foundation classes, and then we have the CIS integration standards. So basically, they are the different ontologies regarding the same objects. So these are the problems that the frame problem causes. And then I'm talking about this because the problem that I saw from Archdaily is exactly the problem of an ontology making. So Archdaily is trying to make up an ontology that everybody should follow, and therefore, because it cannot exhaust all the possibilities, and then we simply fall into the same dilemma that AI has been encountered with many years ago. And then therefore I was thinking, okay, then what is the solution in the contemporary AI, or how do they, what is the solution they propose? So the prominent example, the prominent event of the contemporary AI comes from the Russian mathematician Markov. So Markov proved that in his very simple experiments that for the laws of large numbers to hold, it is not necessary that the variables are dependent or not. So which means for the possibilities, for the probability distribution we observe, it doesn't matter if there's dependency between the variables. And then this means, this implies that, so basically what we need to care about is what to put together so that we can observe instead of the, let's say, the logical implication between those two things that we put together. So it is the matter of, cutting the sequence of letters into the chunks that matters, rather than the causal relation between the first and second letter matters. And then Markov did this. Sorry, Markov did implemented his ideas on the text of a Russian poetry. But then at that time, because the lack of computing power, his work was kind of well, other things. Okay, this is interesting, but it's not really useful at that moment. And then people are questioning. Okay, well, it's beautiful, but then what's the next? But then once we enter this digital age, then we realize that actually Markov's simple idea can become very powerful, especially, for example, how we model the internet. So this is exactly what Google is doing. So Google is not longer care about the content of each web page. It doesn't rank the web page based on the text written in this web page or the title of this web page. It simply looks at what are the hyperlinks pointing towards this web page, and then what are the hyperlinks that leads away from this web page. And then it is essentially a Markov chain, a huge matrix that Markov proposed. And then from this huge matrix, we being able to navigate through our internet. And also, what Markov failed in the beginning now works for this word embedding technique. So the word embedding, which essentially look at each of the word with its enabling words. So basically, we are still cutting this sequence of text into chunks, and then instead of cutting them into 2 by 2, we may cut it with a longer sequences, and then we say that okay, the word at the center of these chunks is equals to the remaining words in the remaining words of this chunk. So basically, we kind of put them together, and then so by this manner, we are actually not looking at what exactly the meaning of each word, but then we are kind of looking at the neighborhood, the context of each of the words, and then by doing this on a large corpus, we managed to numerically represent the meaning of the text, so that, for example, the numerical vector of king plus the numerical vector of mother, then minus the numerical vector of fathers, roughly equals to the numerical vector of queen. So we can do arithmetic operations on words, essentially. And then this is, again, the same story of nowadays a classification with neural networks, for example. So the classification is not about one particular image, but then about a group of images that we put same labels to them. So we say all these images on the left, which is one animal. We say all these images are equals to each other. They represent the same thing. And again, on the right side, all these images are the same. And therefore, the matter becomes, okay, then we are not longer caring about the causal relationship between the counts, but rather the a more subjective way that, okay, we say 1 equals to b, and then this is the thing that we want to put together. So this kind of an inverse manner of how we treat the reality. And then if we look at the computational mechanisms of the contemporary AI, so it's the process of the computation no longer reflects the reality at all. So in fact, it is not the attempt of the neural network to try to replicate our neural behavior, although it may sound like that. Actually, neural networks we can simplify it as logic gates, and then we kind of put in different logic gates together so that the different logic gates constitute to a very complex function. And then this is all the contemporary artificial intelligence is about. It's about the curve fitting. And then we kind of tune these variables of the neural network so that it fits to any functions. And then comparing with our previous attempts where each variable carries a specific semantic meaning, and then the variables of the neural network carries no meanings at all. So they cannot be interpreted in the same way as we did for our previous attempts. And therefore, this comes to these observations comes to this proposal that, okay, if we try to forget about giving a precise definition of those images, if we try to forget about making categories anymore, if we put all these images into a context-based manner, then what can we get? So basically, with this experience, it's the claim that, okay, let's try not to reason about why these things happen, but just try to look at, okay, the pictures and its neighbors. And then, then it comes to the third part, the experiment itself. And then, as I said, actually the experiment it's super, super simple. So the idea is that we have architectural projects, and each of them are uploaded by the authors with a collection of images. So basically, the author says that all these images are equal because they belong to the same project. And then, so my idea was that, okay, then I can apply this manner in a hierarchical order. So for each project, I say, okay, all the images of this project are equal. And then for each image, I can say that, okay, all the patches sampled from these images are equal. And that's it. And then it's a way that, okay, imagine that we are doing text search. Then we are doing image search as of we are doing text search. So we search for certain keywords from the images, and then we get the source image as of, we get the source text from certain keywords. So the experiments begin with crawling lots of data from Archdaily. I forgot the exact number, but roughly 30,000 projects, and then 100,000 of images. So a small portion of them looks like this, and then I do a simple yes/no labeling, so that because I want to focusing on the photos rather than the floor plan drawings as a first step. So I do this yes/no label of maybe 1,000 of pictures, and then the machine learns the rest, and then do the prediction so that I get all these photos nicely. And then after that, this is the simple operation I made for all the photos from Archdaily. So I cut them into these small pieces, and then using the pre-trained neural network, then for each of these small pieces, I get a numerical vector that represents whatever the thing it is containing in these small pieces. It could be the color, it could be the texture, it could be the objects, whatever. And I do a nice panorama on top of it. So this is what this panorama looks like. And if we stay closer, then we see each of these small cells represent a part of the architecture images. And then after that, it's so this panorama works as a small dictionary or as an alphabet from which every image can be spelled. And then after that, so if we have different images, then we do the same process. So images into the small pieces, and these small pieces, each of these small pieces corresponds to a certain location of this panorama. And then for each image, we get a kind of a pattern map and activation map, a signature over this panorama. And then the thing is, and then to comparing images is essentially comparing the similarity of their signatures, and that's it. So, and then for example, we can start saying, okay, I want to search for a whole paragraph of text based on certain keywords, then which is essentially searching for a whole image from these small samples, small patches. Then, for example, I can use these images as the patches, so they contain different styles of beds. I say, okay, this is my keywords, and then gives me those paragraphs that contains these keywords. Or I say, I want the keywords of books and concrete, and then what are the paragraphs that talks about books plus concrete. So and also chairs and concrete, and then these are the stories about chairs and concrete. And then what about bicycles? And then these are the architectural stories about the bicycles. And then what about this? This is, I don't know, some certain, it's a metal pipe, but then it can also be interpreted as a certain a spatial pattern. And then these are the patterns that, architectural paragraphs that talks about these patterns. And also, since I can do, keywords to paragraphs, then I can also do paragraphs to paragraphs simply by comparing, let's say, the frequencies of the words of these two paragraphs, which in this case here, the frequencies of different patches from different source images. Yeah, and then, for example, I took this nice looking picture as the source. I cut it into the small pieces. I get a kind of distribution of its keywords, and then these images are those that have a similar distribution of the same keywords. And then I can do it for living room with a nice chair, and these are all the living room with nice chairs. And then these strange looking stairs, and then these are the similar architectural paragraphs. Yeah. And because I can do it for each of the images, and then it's the same story to do it for the project, because as I said before that each project consists of many photos uploaded by the author, and then basically we think that, okay, we put an equal sign between all these photos, and as of each project is the paragraph, is the text spelled with these photos. Yeah, if we have a closer look of, so this is a panorama of all these photos, and if we have a closer look, then this is the keywords that shows up in all the architectural projects. And then again, I can do project search in a very similar manner. So simply feed this dictionary a certain keywords I'm interested in, and then by looking at the frequencies, I get those architectural projects that has the similar distribution. Yeah, and then so I did this a few weeks ago. So basically trying to implement it on an internet as well. Okay, so I will stop and share screen here. I will put this in order. So basically, this is the panorama you saw from the presentation, and then these are the keywords that kind of extracted from all the architectural projects. And then here, then I can simply say, okay, I want this one. This one looks good. and then perhaps this one as well, and I can change it to a different color so that the computer knows, okay, I want the intersection of these two rather than the union of these two. It depends on what I want. And then, so by doing this, then it gives me a list of projects that basically contains both of these two keywords. So for example, if I go to the bottom, sorry, and you see here is this vertical elements like small woods. And then what is the other one I was searching for? Yeah, and then these hallways. Yeah, here, for example. And then yeah, I can play with it so that I get many different things. Oops. Yeah, obviously the combination of these two gives very little results. Yeah. Yeah, but then you get the idea. Oops, sorry. Let's start sharing screens. Share. Yeah. So that's basically it. The small experiment I would like to present to you, and then it's online and it's in a very primitive stage, and then hopefully you find it interesting to play with, and if not, then it's okay. Yeah, thank you. Yes.